Hi, welcome back to the Shiko Math Practice Lab, Learning Through Practicing. And we are in the unit for the exponential growth and the decay. This is our second practice set. And in this practice set, and we're going to specifically practice some problems about exponential growth and decay. And specifically, we're going to focus on the double life and the half life type of the problems, and to see how can we simplify our, to see maybe we can simplify our formula for the double life and the half lives here. Okay, and let's see here. So, okay, so this is our second video. We're going to talk about the double life and the half-life for the exponential growth. Okay, let's start to take a look at our problems here. Okay, so the first problem here is will tell you a common inhabitant of the human intestines is the E. coli. Cells of this bacterium in a very nutritious medium divided into two cells for every 20 minutes. And then the initial of the culture is 50 cells. And I want to find the relative growth rate here. Okay, so in here, okay, so it tells us, every, so it tells us here, it turns into the two cells. That means every time they double it in every 20 minutes. And then initially we have 50 cells here. So how do we do it? Okay, so let's take a look for this type of the problem here. Okay, so we still follow, we still follow this is our formula, right? PT is equal to the P0 and the EKT here. And it says for the 20 minutes, right, I double every time 20 minutes, I start with 50 cells here. And then I want to find what? I want to find the relative rate, right? The relative rate. So I want to find this K value here. Okay, so now this is the 50, and then the 20 minutes here. So this is my K. So 20 minutes is the 1/3 of an hour. So I will put the T is equal to 1/3 here. All right, and I said every 20 minutes it will double. So that means 50 going to double to what? Double to 100. So if you solve it, then you will find the 2 is equal to EK and over 3, right? Now I can solve for K. I will take the natural log of both sides. So it's natural log of 2 and the K over 3. And then you can just say K is equal to the natural log of 2 for the 3. And so this one, if you like, you can say this is 2 to the 3rd power, right? Because you can use the exponential property, move these constants inside. Okay, so now let's try to rewrite this. So the PT is equal to the P0 and the E, all right? So the K is a natural log 2 to the 3rd, and you have what? You have a T here, okay? So you can use the natural log property one more time because this T is T times natural logs, right? So you can put this one back to the exponents again. So it will be to the ETs here, right? So the natural log 2 to the 3t, because you can treat this as times t's, right? So that means you move to the exponent. Then these two cancel, all right? So these two cancel because they are the inverse functions. Now your formula for the double life will just be your initial value. And then here, this is the 2, 3t. Okay, or if you want to you can simplify this ones here. This is the 2. Then the 3t is really is t over what? Is 1 over 3, right? So why the reason I want to do that? Because now I know my double life formula. I can write it as the pt is equal to the P0 and 2, that means double life, right? Then in here I can have T and T star. So what is this T star? T star is the one, so the T star, this is the time for the things to double. Okay, so this formula here, so this double life formula will be pretty easy, right? So you just instead of the e to the exponents, it's just the 2. So the same way we can find the half-life. So it's exactly the same way we can derive it. So the half-life here, the pt, you can do the same proof. You will find that this is, instead of 2, you can say this is 1/2. And then you have a t and a t star here. So the same way, right? So what is this t star here? So this t star is what is the time for things to have, right? So if the if they die out half, every 2 hours, then your t star it will be 2. Okay. All right, so now that's why here we say, okay, the first problem here, we did a little bit of too much. So they want to just ask to find the relative rate. So the relative rate is natural log 2/3. So the part B say is find the expression for the number of cells after t hours. That's just what we derived here. So this is the pt equal to the p0, right? And then is 2. Then you can put a t over t star. So t star is 1/3. That's how do you get a p0, 2. This is 3 t's. Yeah. Okay. All right. So now let's take a look at the next part here. It said find the number of the cells after the 6 hours. Okay. So I know my pt equal to the P0 and the 2, the 3 t's, right? So what is my P0 here is 50s, right? Then this is a 2, then this is a 3, 6 hours, you just times 6. Okay, so that's so it's 50 times the 6, so this will be 131,072. 0. That's what I have here. Okay, so now the part D, we did this this type of the problem from our first video a lot. Find the rate of the change after 6 hours. So that's what I'm looking for, dp dt, right? So this is a p prime t, and this one is defined as k times p. Okay, so what is k? K we just did in the part A, so it's 2 to the 3rd power natural log. So what is this p? This p is the value here, right? So this is here, so it's this value. Is the value after what? It's after the 6 hours. So at times 131,07200. And this one will give us a pretty big number. So this is a 272,55656. Okay, so now part E here is how long will take the population to reach the 1 million, right? So here you can just say the 1 million, so it's 60. It's start out 50s, right? And then you have 2. This is 3t. Okay, and then you'll be able to kind of divide by 50, and so this one divided by 50, you will have 20000, right? Okay, so I think I have one extra zero here. So that basically you just okay, so you just divide it by, and then so this will be 2 to 3t. Then you take the natural log of both sides, so you will get a 3t. The natural log of 2 is equal to the natural log. Okay, I get that one right. So okay, so now you can find the t approximately to the 4.76 hours. Wow, this Ebola bacteria certainly grow very fast, right? So after 6 hours, you know that you can reach 1 million cells there. Okay, now let's take a look at the second example here. Okay, so second example is to tell you, I think it is a strontium. Okay, never know what is this chemical before, but anyway, so it said strontium 90 has a half-life of 28 days, and so a sample has mass 50 milligram initially. Find the formula for the mass remaining after t years. Okay, so remember this is the half-life we did from the previous the problems. We know the half-life formula is what? So it's PT equal to P0. Instead of the 2, what I have here, I have 1/2. And then here is T over what? T stars, right? Okay, so now let's take a look. We'll be able to write this one. So this is PT. So what is my initial here? So the initials here is 50 milligram. And what is my T star? T star is how long to get a half-life is 28 days here. Okay, so I will say this is 50, then this is 1/2, then this is T divided by what? Divided by 28, right? Okay, that's pretty easy. Okay, now let's take a look at part B here. Okay, part B said, what are the mass remaining after 40 days? Okay, after 40 days, you are looking for P40s, right? So this will be 50. This is 1/2. Then this is 40 over what? 28. Then you can put it into a calculator and you can get this is about 18.6 milligram left here. Okay, so part C, we tell you how long does it take the sample to decay to a mass of the 2. That means the 2 is going to equal to 50, 1/2 T the 28. So divide the 50 both sides, so you will get a 1 over 25 is equal to 1/2 T the 28. Then you can take the natural log, both sides is 25 is equal to T the 28 and natural log 1/2, right? So you can take natural log both sides. So now the T, what is the T will be equal to is equal to negative natural log 1/2, 28, and the natural log 1 over 25, right? Okay, good. And now you will find that this is about 130 days. Okay, so you put it into a calculator and you get it about 130 days. Okay, so let's take a look at another ones here. Okay, so another one is very similar to the, to the half-life ones here. Okay, so the number 6 here, ask us what is the half-life of cesium? 137 is 30 years. Suppose we have a 100 milligram sample. What is the mass remaining? Okay, so this one is easy, right? We already know. So the mass remaining PT is equal to the initial. So it's what is here? It's 100. Because it's a half-life, so it's 1/2. So where is my T stars here? T star is what? It's 30s, right? So I have a T over 30 here. Right, so pretty easy if you can remember, so if you know how to derive it, to remember the half-life and the double life. The part B is here is how much of the sample remains after 100 years. So you are looking for P100. So this is 1/2. This is 1/2. And then here is what? 100 over what? 100 over 30. And then you put it into your calculator. You will get about 9.92 milligram left here. Okay. Part C, how long does it take the sample to decay to a mass 1 milligram? So it's the same old problems like we did before. So 1 is equal to the 100. Then this is 1/2 T to the 30s, right? So it's 1 over 100 is equal to the 1/2 T to the 30. Now, natural log 1 over 100 is equal to the T30 natural log 1/2. So what is my T values here? T value will be equal to natural log 1/2 and the 30. This is natural log 1 over 100. And I put it into the calculator. I get the number is very close to 199.3 years. Okay, so for the problem number 6, if you can remember the half-life formula, it's very, very straightforward, right? So it's a half-life and the double life formula. So they can simplify that from the general exponential decay to the double life and the half-life. Okay, let's take a look at the other ones here. The other ones here is a sample treating and decayed to the 94.5%. Okay, so that means I decayed to 94.5% after 1 year. Now I'm looking for what is the half-life of this. Okay, so let's take a look. So 94.5, right? So that means my P1 after 1 year. So this is P0 EK. T is 1, right? T is 1. Okay, so let's say T is 1. Okay, so here this is 1. Okay, so now it's decayed to 94.5 of its original. So this is 0.945 P0 equal to the P0 EK, right? So P0 cancel. So you can 945 equal to the EK here. So what is your K here? It's a natural log 0.945. Okay, so now I'm looking for what? I want to find the half-life. So half-life, that means, how long take it, right? So I'm looking for the PT. Okay, it's a half-life. That means what? It's a half of the what? Half of the PZ, I'm sorry to hear, I should say here. Okay, so that's why I said that the half-life, that means, the half of the, okay, so half of the P0s, right, will be equal to what? Will be equal to the P0. Then here you have a natural log of 0.945. and you times what? You times t, right? So we'll give you the half-life, right? Because P0, and this is half of P0. So P0 can cancel. So this is 1/2 E, and the natural log times t. So you can put this is natural log 0.945 to the t. The natural log and the e can cancel. So you will have 1/2 is equal to the 0.945 t. Then you take the natural log of both sides. So you have 1/2 is equal to the t natural log 0.945. So what is my t's here? T will just be natural log 0.945 and the natural log 1/2. Right, so if you put it into the calculator, you will get a t is approximately to the 12.25. Okay, so now let's say how long will it take the sample to decay to the 20%. So it's the same thing. Instead of half-life, 20% is what? Is 1/5. Your original P0 will be equal to the P0 and the E to the natural log 0.945 to the t's, right? So P0 cancel, and then this one you can do, this is natural log 0.945 to the t. So natural log cancel. So you will have 1/5 equal to the 0.945 t. So you do the same way, you take the natural log of both sides, so it's natural log 1/5 equal to the t natural log 0.945. Correct? So what is the t's here? T will just be equal to the natural log of 0.945 to the natural log of 1/5. The t is equal to the 28.45 years. Okay. So this is our second video. We are talking about a very special type of the exponential growth and decay. We call this the double life and the half-life here. All right. So here is the formula we have in here. We said that this is the, this is the double life, and this is a double life, and this is a half-life. So the formula become pretty simple. It's just be the 2 and 1/2. All right. Okay, that's it. And let's follow our video number 2. So now let's take a look at the video. We're going to the video number 3. We're going to talk about a special kind of application. We call this the Newton's cooling laws here. Okay, we're looking forward to talk to you in our next videos here. Okay, bye.